Alright, hello everyone. And in this video, we are specifically looking at different kinds of forces that we are most likely to encounter during our study of physical systems in an IB course. Now, when we dealt with resultant forces and spoke about how forces act to change the course of motion, right? Uh, Changing its state of rest or motion and all that, we use Newton's laws, right? And the most important amongst them was F equals to ma. So anytime you have forces acting on a system, you are most likely to look at a resultant effect of that force. So always remember, never lose sight of this term, right? When you're using F equals to ma. Even if you're considering just one force, then what you are actually doing is you are negating the presence of other forces. So, for example, in a given physical phenomena, there is one force that dominates over other forces. So, we are more likely to concentrate over that dominant force and understand how that affects the system in general. All right. So, let's say, for instance, I take a simple example, say motion under gravity. All right. Motion under gravity. We all know what this entails. We have discussed this a little bit when we were talking about energy, right? So if you look at the energy production videos or energy changes video, you will come to terms with this. But even if I look at motion under gravity from a force aspect, we can actually arrive at the same conclusions that we had from the energy considerations, which is what physics is about. You can have parallel approaches to a given physical phenomena, and you would still end up having the same conclusion, right? So, motion under gravity, very simply put, is nothing but, say, an object, point object, falling vertically downwards on account of the resultant force acting on it. And this resultant force is W, which we write as mg, where m is the mass and g is the acceleration due to gravity. All right. Now, therefore, this is the reiteration of this equation and nothing else. W equals to mg represents F equals to ma, where a is equal to g because that is the acceleration with which an object falls towards the earth as the earth pulls the object towards it. All right, it's pretty straightforward there. Now, obviously, as it falls downwards, it accelerates. So you can use equations of motion to study them. If I just look back again for an object falling vertically downwards, V equals to U plus GT, right? V square to U square plus 2GS, where S represents the displacement. Sorry. S equals to UT plus half GT square. Right? So these are the equations of motion that you can use in order to understand motion under gravity. Right. Now, another deviant phenomena that we study underneath the same banner of motion under gravity is that when we throw an object at an angle with respect to the ground, by now you're aware that whenever we are talking about vectors making angles with the vertical or the horizontal, we are inching towards nothing but vector resolution. So let's see. So we have say an object as being thrown in this direction, and this is the ground line. Well, not quite. Let's get rid of this. Say roughly this is the ground line. Just extend it a little bit. All right. Now this direction is the initial direction that this object is projected with. So obviously, if an object is getting displaced in a given direction, right, the displacement and velocity that it has will also be in the same direction. So this represents the initial velocity with which the object is being thrown. And this is the angle that it makes with the horizontal. Now what we see, of course, we have all thrown objects. We all played ball with our friends, cousins, dad. That's what it looks like. Not exactly the path, there is a little deviation over here, but it's a smooth curve, right? A quadratic curve that we see. So this represents, by the way, again, I've seen many people getting confused with this, though I don't know why. This represents the trajectory of this object, which means the path that this object follows, right? This is not a graph. A graph is a mathematical representation of how two variables, right? How two variables are related functionally with each other. Like, is one directly proportional to the other? Is one inversely proportional to the other? Is one the square of the other? Is one the square root of the other? And so on and so forth. Or if one is an exponential variation of the other. So that is the graph. This, on the other hand, represents the path that the object travels in under the effect of gravity. All right? So this is tangential at this point. Now, the important thing that we see over here is that at this point, the object is over here. So the velocity is actually in this direction. Exactly there. Let's tilt it a little bit. The velocity is actually in this direction. All right. So there is a clear deviation if I draw the line over here, and this is the line over here. So that means there is a difference, right? They are not parallel to each other, which means the velocity's direction has changed, which makes sense, right? The direction of the path changes because of the change in the direction of the velocity of the object. All right. So there's one more takeaway point from this exercise that we see here. All right. And what is it? It is that the path of an object can be said to change when the direction of velocity at each point is different, right? Had this been parallel to this, that would have meant that this is going on along the same path. Maybe the velocity's magnitude has reduced, but its direction remains unchanged. So it would move along a roughly straight line trajectory. All right. Again, no confusion with what it implies in terms of having a straight line speed time or velocity time graph. I am not talking about a graph. I am just talking about the effect of how change in the direction of velocity, right? Change in the direction of velocity can be interpreted or can be seen as as a reason behind the characteristic. And what characteristic is that? Characteristic of the direction of the path changing, the path curving, the path turning. So in all of that, the main focus is that, so over here the velocity will be in this direction. So over here the velocity will be in this direction, right? So it's at roughly the highest point. So roughly the highest point. So over here, they cannot go up any further, right? So there can't be a velocity which kind of points in the upward direction. So all the direction velocity that it has at this position is parallel to the ground, which means horizontal. And there again, all right. So at each point, we see that the velocity's direction is changing. All right. Now, what about the magnitude? I've focused so much till now on the direction. So what about the magnitude, right? Remember that this motion is taking place under gravity. All right. Now, if I ask someone in which direction the gravity acts, they would promptly reply downwards, right? Vertically downwards. All right. That's why I've made sort of a vertical axis so that we have a rough overview about the direction. So in this case, we see the velocity with which this object is being projected as u, and this makes an angle theta with the horizontal. The first thing to do is find the horizontal, say, component. So that is u cos theta, right? Now we are well aware. So just drop so we drop a dotted line. So this bit is the base of the triangle. This is a right angle triangle, or the adjacent. This is the opposite. So adjacent by hypotenuse gives me cos. So adjacent is equals to hypotenuse times cos theta. That's what we get. So the vertical component is u sine theta. All right. Okay, we're good to go now. So therefore we have u cos theta, u sine theta as the initial vertical and the horizontal components. All right. Now let's be careful. So gravity is acting on the system, right? Which is the reason that at every point it is still being pulled down by the earth. All right. But it always has a horizontal component which is not being affected by any other force. Okay. So unaffected by external forces. Affected by gravity. Makes sense, right? Because gravity will only act on that part of the system wherein it's trying to move in the vertical direction. And we know that if we divide the vector into components, it helps us divide the motion into two independent parts. One part catering to the vertical direction and the other part catering to the horizontal direction generally, as is the case over here as well. So this vertical direction is now acting separate. It is acting sort of independent of the horizontal because the horizontal does not come under the purview of gravity. This component would never be affected by gravity because gravity is acting downwards like this. At this point, the weight, or at any point, the weight is always acting vertically downwards. So it will only affect u sine theta, right? So here, in case of u sine theta, we can actually go back and use these equations, which is exactly why I had written them over here in the first place. So we can use our final velocities and initial velocities depending on the vertical component of this motion that we have considered. For example, at the highest point, say P is the highest point. So at P, we have vertical component going down to 0. So if instead of drawing these vectors which represent the resultant velocity at each point, which means there is a vertical here and a horizontal, all right? Means there's a vertical here and a horizontal, and there is no vertical here. Now you see over here, although it's not drawn to scale, this and this, if you compare to this, they are all progressively smaller, right? Which makes sense because we all know that as an object moves upwards vertically, its velocity reduces, right? But this does not show any conceivable change. The horizontal does not show any conceivable change because the horizontal doesn't experience a force, right? So it remains the same throughout. So even over here, if we look at this, the vertical is a little down. The horizontal, roughly the same. 1, 2, 3, 4, they're all equal because the horizontal is not affected by any force. So its velocity is not changing. Newton's first law of motion, if you haven't figured that out already. An object in state of rest or motion continues to be so until an external resultant force acts upon it. So by using our idea of vector resultants, we have separated the motion into two separate components, and therefore we can treat one independent of the other. So the vertical being affected by gravity shows a variation, right? So if you were to draw a speed time graph showing the change of the vertical component of the velocity, it would show a similar variation as, say, for example, an object simply being thrown upwards or falling downwards under the effect of gravity. So, but it would be only a change in this u sine theta that we are talking about, nothing else, right? Whereas u cos theta with respect to time would actually represent a graph that looks like this because it doesn't change, right? It doesn't change, it remains constant. And u sine theta would actually show a variation much like how velocity varies. So it would go from, if it's being thrown upwards, so its velocity will reduce from maximum. So it's likely to be like this. This is the velocity of projection. Velocity reduces to 0 at the highest point, and then it keeps increasing. But in the negative direction, of course, because we know that when an object falls downwards, we generally associate all negative you know, quantities to it. So if it had a velocity of +5 while it's moving up, while it's going back down, that same velocity will be represented by -5. All right, which makes sense because uh, in the graphical equations video we saw that this represents a negative gradient. right? And negative gradient here implies in a speed time graph acceleration, which is g. It also makes sense because g is always acting downwards, which means g is always negative, right? So it remains negative throughout the motion. So this is negative, this is also negative. This represents acceleration, which is also negative because it is not, it does not imply, again, another concept that I would like to touch upon here. Negative acceleration can be interpreted as deceleration or acceleration in a direction of motion which is opposite to the previous motion that was taking place. Clear? So, for example, in this case, the negative gradient actually represents deceleration because as it's moving up, the velocity is reducing from a maximum to zero. Here, this negative gradient is representing acceleration. But why? Because it's representing acceleration in the opposite direction to this. In this case, it was moving up. In this case, it's going down. So it's still negative. It retains its negative character, but it changes the way it affects the motion, right? So at P, the vertical component is 0. So for the vertical component, I can actually write something like this. 0 equals to u sine theta minus gt. So this represents the equation of motion for the object moving from this point, say O, to P. So T equals to u sine theta by g. So time taken to reach maximum height. All right. And the total time of flight, because it's in a gravitational force field, is twice this, because gravity acts in the same manner on its way back down, and also for other reasons which we shall discuss in greater detail when we are dealing with fields and gravitation. It's units 6 and 10 respectively in your textbook, so cross, right? When we deal with that, we will focus more on this. So twice of this t is equals to t, which is the total time of flight. Okay. Now, similarly, using these equations again and again, you will be able to figure out maximum height, which is u square sine square theta by 2g. Or you can also figure out the horizontal range, which means how much distance it covers as it moves in the horizontal direction. All right. And that is u square sine 2 theta by g. All right. So this you can try at home and figure out how these come into being. So the important takeaway again is that the horizontal component over here does not experience a force, but the vertical component is affected by gravity, and hence I can actually consider the vertical portion of this motion to be pretty similar to how it was in case of just an object falling under gravity vertically downwards, or an object being thrown upwards uh, under gravity, right? So that's all for today's video. I'll see you in the next.